So, hello, my name is Polina Bungina. I work at Zalando, which is a European e-commerce platform. I am a senior software engineer in a team which is responsible for internal database as a service platform. And today I want to share with you our findings and experience when adopting and supporting our internal CDC solution based on logical decoding. So, as I said, today we will look into the logical decoding in PostgreSQL and actually the hazards behind it. And the plan for today is just to quickly look into what CDC is, what are the approaches for PostgreSQL, and then go directly to the logical decoding, the concepts behind it, and the hazards which it may bring to you. So first, CDC is essentially change data capture. It's a set of design patterns which used to track changes that occur in your data, when and what kind of changes, and then notify the external systems about those, which basically helps you to maintain consistency across all of those systems. For Postgres, we mainly have three approaches to do that. First is to run queries against dedicated timestamp columns, such as created at or updated at. Then you can use old good triggers just to create them for the events you want to be notified about. And then the maybe most modern and advanced solution is to use logical decoding, which I want to talk about today. So logical decoding is effectively a process of extracting all changes persisted to write-ahead log back to the format which is human readable or the application friendly and can be further used without knowing the internal state or structure of the database. And my idea, what I want to tell you today is that even though this approach is very advanced and it actually enables a lot of new use cases for you, it can be dangerous. And it's rather complex. It requires you to understand all the implementation details, maybe not all, but the most important that can be dangerous. And it's not only about database administrators, but also about the end users. And to cover those, I would like to split my talk into three parts, talking about the three main components, so to say, of the logical decoding. And we will start with the decoding process itself. What is important to know is that PostgreSQL cluster has a single write-ahead log. It's for everything, not split it per database or per table. And the second part, a bit more tricky, but you need to remember that by default, all transactions are sent to the consumer only on commit. Of course, you may say that since PostgreSQL 14, there's a streaming of in-progress transactions mode, but by default, it's only implemented if your consumer is another PostgreSQL instance. But of course, for other implementations for your end applications, you would need to implement it yourself. And it's rather questionable if you want to implement it and store data before they are actually committed, before this data is actually committed on your application side, or it's better to keep it on the database side. This way, I will concentrate on the default behavior. And to better understand why it's dangerous, I would like to quickly look into the process. And for every connection, for logical decoding, there's a separate wall sender process point, which reads sequentially all the wall records and decode each of those and store those in a specific buffer. You basically queues it in a reorder buffer. When a commit message is reached and decoded, then the associated transaction starts to be replayed And for every record, there's a specific callback code, which is basically the place where the customization takes place. And for example, output plugins, which implement this customization, can transform your data into any format you want it to be. And also what is important on this step, there's a filtering taking place. The so-called publication define if you need to stream this data further or it can be filtered out. And why it is so important to know that is, imagine you have transaction number 1, which is opened, and then suddenly another transaction comes, and there is this transaction is very write intensive. So, for example, it inserts a lot of data, and then it commits. This way, it doesn't matter how quickly you commit the first transaction. Your receiver will first receive all the changes from the second transaction, which needs to be decoded, replayed, filtered, and only after that, the changes from your first transaction will be received. As I said, there is a reorder buffer, and it's stored in memory, but of course, memory is not endless, and there's a limit after reaching which all the decoded changes not yet committed will be spilled to disk to a specific directory. More insights on the process can be found in the pgstat replication slots system view. There you can find cumulative information about how much was decoded in general, or what is more important, how much was spilled. And this is probably, and I think, it's worth monitoring. And this is available since Postgres 14. Another important nuance worth knowing is that for every decoding process, there's a separate will send response, consequently a separate decoding process happening. You would allocate every time this logical decoding work amount of memory and spill decoded data for each process, and each of them reads the same wall record stream, so does the same work. And another thing worth understanding is that it's actually very difficult to scale this by just scaling your instance vertically, because each decoding process will only use a single CPU core. And as an example, how to easily get trapped by those nuances, those hazards, is our favorite online vacuum full and cluster tool called pgrepack. And actually its initial step is to copy all the data from the target table to a so-called temporary table, which is, of course, a very write-intensive operation, and it's done in a single transaction. Then think of your database of your table as a very big table. It means that, of course, you will copy a lot of data, and I think you probably have full page writes enabled. Consequently, there's a lot of data written to wall, so pgwall directory grows. Also, memory is filled with this reorder buffer, and all the decoded changes starts to be spilled to disk. So this specific directory with spill fast also grows. So your free disk space decreases very rapidly. And what is the worst thing here is that it's not even needed for your consumer. It all is decoded, all the resources are used. But of course, as this is a temporary table, you do not even need this. So it also filtered out and never sent. Then to the second part, and I think the most important part to understand, is the logical replication slot. And this is essentially just a structure that defines the state of the associated consumer. And defines the resources still needed for it. And by the resources, I mean write-ahead log and tuples affecting system catalog that also needed for the decoding operation. It is important to know that slot is persistent, it's crash safe, and it exists independently of the connection using it. So to say, if you disconnect, your client slot stays in place, but just does not update its state and does not move the positions which define the required resources. More insights on the process can be found in PG Replication slots system view. It gives you information about whether the slot is active. So if a wall sender is running for this connection, so the connection is established, and the positions which I mentioned, which define the resources still needed. Oldest catalog xmin is about oldest transaction affecting the catalog, system catalog, which is still needed. Then restart LSN is the oldest write-ahead log still needed. And the third one, and very important one, is the consumer confirmed the position up to which the consumer confirmed processing the data. This is called confirmed flush LSN. Why it is important to know that it's persistent, the slot, is because just think of the situation when you disconnected from the slot and then connected to it again and want to continue your decoding process. For that, you define the starting point, which you probably have saved locally. And the thing is that if persistent data of the slot defines a position newer than what you provided, your position will be disregarded and the saved position will be used because it's essentially your actual state. So it's important to properly implement your client and properly store the current state on your side. And about the part that it defines the resources still needed, think of the situation when you have a slot that you disconnected from and it stops at updating its state. So Postgres thinks that all the resources created after this position are still needed. And it essentially means that your PG wall directory will grow endlessly before you connect to the slot again and start to update its state. And it's actually very easy to get into this situation. We've seen a lot of cases when people were thinking they're doing better, but in fact, they were just creating an inactive slot. For example, they could downscale their consumers for cost-saving reasons over the weekend or after performing some tests and waiting for the production launch and many, many other situations. But it all is about the situation when slot is not advanced and PG wall just accumulating in the PG wall directory and disk space is running out. So one minor but actually very important thing about those who make use of Patroni. Patroni has a nice feature of logical slots failover, and for that you will define slots in your Patroni configuration as the permanent slots. And when your users, even when they remember to delete slots, if the slot is still in the Patroni configuration, it will be immediately recreated. For that reason, it's worth thinking about any kind of interfaces for Patroni configuration for your users, or even better, some automation around that. And users will, of course, ask questions about the necessity of the slot deletion. And the first will be, I'm not producing any changes to for my publication. It's easy. As I said, wall is a single stream of changes for the whole cluster. And it's not necessary if you produce changes for your publication or for anything else in your database. It just writes all changes into a single write-ahead log And if you're not deleting slot, write-ahead log size just grows. The more sophisticated question would be, they would say they are not expecting any write activity at all during the weekends. It's almost always not true, because you may not be aware of the scheduled maintenance task, or some minor write activity can cause an auto vacuum to kick in. And this all, any write activity activates the process, which after an archive timeout elapsed, of switching the wall segment, so that the database starts to write to a new file. And tricky part here is that every file, regardless how much you read into it, will be of the same size, which is 16 megabytes by default, or the size you defined on the initialization stage. And it's not only about slot being inactive to have problems. You also can have your slot just moving very slowly in comparison to how quickly you produce writes. And one of the reasons for that, it can be that your consumer just underperforming. For that, just first, of course, tune your consumer application and remember to make use of publications, or actually filtering, not only on the table or schema, but also on the action you want to publish. And the last thing about slots is failover. Of course, if your database fails over to a new instance, you want to continue decoding process and not to miss any changes. Unfortunately, there is no out-of-the-box solution yet, even though we're expecting it in the closest major release. But for now, there are a couple of solutions for that. If you are using RDS or any system that uses file system replication, that's not a problem for you. For others, you can use Patroni logical source failover mechanism, as I've mentioned, which has its cons. Because of the function used internally, or the more advanced solution, PG failover slots extension. And now to the last part, the replication protocol. Just quick overview of how it looks like. There's a message with data, with changes sent, and actually, apart from data, it also contains the position in the write-ahead log, which is associated with this change, and this position should be used by consumer to update its internal state. Then the consumer is obliged to respond back to the wall sender and just inform about its current state, which is in its turn used by wall sender to update the replication slot state. And looking into this schema, you would probably say that if there is no data, if there is nothing produced in the publication, and no changes produced for the publication, slot will not be moved forward. And for that reason, there's a special message called primary keep alive message, which sends the current position of the wall sender decoder to consumer. And this position can also be used for updating the internal state and respond back to the wall sender to allow replication slot to be advanced. But unfortunately, it's quite often forgotten. And for example, up until to the latest version of, not the latest, but one of the latest versions of PGJ DBC, there was such an oversight that this message was received, but the position was never used to update the internal state of the consumer. And the position reported back to wall sender was stale, and replication slot was not moved forward. And yeah, it's basically created a lot of problems for occupying more and more disk space with walls. But another problem was about the endless shutdown. You see, when you shut down Postgres, not in immediate but any other mode, it will wait for clean shutdown, and clean shutdown means that all consumers reported back to their wall senders that they received changes up until the checkpoint, shutdown checkpoint position. And because of the oversight I mentioned, it wasn't happening, and Postgres was just endlessly shutting down. One of our engineers at Zalando fixed this in the 42.7 version of PGJ-DBC. And also a couple of years ago, it was also fixed by another Zalando engineer in PsychoPG2. What was painful for us? Actually, because PGJ-DBC is used by our favorite CDC tool called Debezium, so it hits us very much. This is pretty much it. As a conclusion, I would like to just sum all the said things up. First, use this nice technology cautiously, beware of the hazards, and make sure you understand how it works. Also monitor the slot state, if it's active, if it is advancing, and also check your free disk space. You probably already do this, but remember about this special directory for spill files. Always delete unused slots, not leave them behind. Another thing I've not mentioned, but also very important, know your workload. And sometimes it can be better to use the old good solution based on triggers, for example, PGQ. It may happen that it will create less problems for you. It will be easier to maintain. And lastly, just make sure that you use the proper protocol implementation. Remember about the story about PGJ-DBC. So that's pretty much it. Thank you for your attention, and I will be happy to answer your questions.